Hello and welcome to Calculus. Hello and welcome back to Calculus 3. There we go. See? We are starting chapter 15. Much better now with voice. And this is on functions. Functions of several variables. We'll start with 2. You can have as many variables as you need. The idea of the function, which you learned long time ago, either in algebra or pre-calculus, whatever your course was called, was that the function is a rule which assigns to each x in the domain a unique y in the range. Now for Calculus 3, we have two-dimensional input and a one-dimensional output. Now, what does that look like? Your domain is the floor, the xy coordinate system. And your range is the z, is the height. So, if I have some object, right, some surface, every point on top of that surface is calculated by a formula in which you get to plug in the xy location from the floor. So the z is equal to f of xy. This is the notation. This would be your 2D input, and this would be your 1D output, all together creating thru-dimensional XYZ realm. The block diagram for something like this would be x goes in, y goes in, function operates on it, z comes out. Graphical representation for something like this would be you have xy, and then there is some kind of a domain. And then you have axis z. There will be a random point somewhere that is in the domain, point xy, which will map onto some point z using function f. As an example, I can define function xy to be x cubed y minus 3x plus 2 over y. So this would be an example of the function. And this is a thru-dimensional function because you have x, y as input, and then f of y, z, we said that's your z. Just like your f of x used to be y, now f of xy is z. So if I want to calculate the function at, let's say, I don't know, 1, 2, you will just plug in 1 for x and 2 for y and just plow through calculation. So it will be 1 cubed times 2 minus 3 times 1 plus 2 divided by 2 This is 2 minus 3 plus 1. Oh, look at that, is 0. So you are creating the point 1, 2, 0. If we calculate at a different value, say 3, 4, 3, 4, then we have 3 cubed times 4, I'm going to regret this, minus 3 times 3, plus 2 over 4. This is 3 times 3 is 27. 27 double double, that's 104. Minus 9 plus 1/2. 104 minus 9, that's a 95.5. So the point is 3, 4, 95.5, or 95.5. So as you can see, not much has changed from your pre-calculus definition for 2D function. Your 3D function has the same feature of computing the z value if you have x and y given to you. Domain is still very important. We want to know if there are any values that are forbidden for us to use. And the rules are exactly the same as you had in your pre-calc 1. For instance, if you look at the fxy, which particular value is bad? What do you mean 0? 0 for y is bad. That is actually infinitely many points, right? Y is equal to 0 on the entire x-axis. You are not allowed to pick any point on x-axis, and that's infinitely many of them. So what is the domain of this function? Domain of this function are all points in xy plane except x-axis. So for this particular problem here, the domain is all points in R2. This is the way to say all of the points of xy plane, except points along x-axis, which is right a comma 0. So we are excluding all of the points on x-axis because all of those points have y equals 0 coordinate, and that would make one of the terms of our function explode, so we don't want that. All right, so let's write the formal definition of the function, which is the one that will probably show on your exam 2, because this is exam, right? This is material for exam 2. So definition of a function. And I'll put 3D over here so we know it's, well, you know what, it's better if I just write z equals f of x, y, so we know exactly what the definition is for. So function is a function z equals f of x, y is a rule which assigns to each point xy in the domain a unique z in the range. This is identical definition to your 2D function, except their domain was one-dimensional, now domain is two-dimensional. So that's the definition of a function. And you see that the input, the domain, is two-dimensional, x comma y, and your output is one-dimensional, just a z value, which I have outlined in both of these graphs, that you have a two-dimensional input and one-dimensional output. So to talk a little bit more about domain, because it's important. Domain. Domain is the set of all points such that value z, well, I should say all points x, y, x comma y, such that value z can be computed. So think of a function f of xy equals square root of xy minus 3, let's say. This is the function. Now, what is the domain? What should I do?
Coming back.
Okay. What should I do?
I can't.
Well, how do we find the domain for?
Well, x and y can't be negative or less than. Or they can both be negative. Yeah.
Ah, see?
But they can't be less than 3.
So is there an easy easy way to write all of that in math? Like, what is the requirement for square root so you can compute it? Okay, so how do I write that mathematically? The argument of the square root can't be negative.
Say the function xy minus 3 cannot be negative.
So how do I write that mathematically?
It must be greater than 0.
Also equal,
Greater
right?
than or equal to 0.
Yes. Because if it's equal to 0, it's still okay. Square root of 0 is 0. So it's just non-negative.
You drag that to the other side.
So all we need to do is to solve this inequality. Right? For ln is the same thing, except no equal. Right? Ln is only taking positive numbers. Square root is taking positive numbers and 0. Right? So over here, I have now xy greater or equal than 3, and y is greater or equal than 3 over x. This is something that I can actually graph, and I can shade the regions that contain points which I can use, and regions that contain points that I cannot use, right? So if I graph this, we know this is like a graph of 1 over x. So it should look something like this. and now I need to shade. I hope that you see that this function divides all of the space in three regions. There is a region that is in there, right? So this is like region number 1. Then there is a region that it's in this peanut over here, right? That goes forever. It doesn't actually end, so come on. So like this, that's region number 2. And finally, there is a region over here as a region 3. So these two graphs partitioned all of the space into 3 regions. I get to shade 1, 2, or all 3, right? So if you look at the value region number 2, and you pick value 0, 0, because you always go and calculate 0, 0 first. That's the easiest one to compute. So you pick 0, 0, and you plug that in your original equation, you get 0 times 0 is 0, minus 3 is negative 3, square root of negative 3, not real, right? And then if either of the x or y is 0, we would have the same, which means any of the x's. So that one eliminates 2 as a shaded region. And now you just have to take a look at a single point from region 1 and region 3, and then either reject them or shade them. So pick something in region 3. Well, how about point 4, 4? That's in region 3. 4, 4. So 4 times 4 is 16, minus 3 is 13. Square root of 13, that's great. So region 3 is definitely good region. So we would shade this part as the domain. You will have the same thing for region 1, because negative 4 times negative 4 is, again, positive 16 minus 3 is root 13. That's all good. So we just shaded the infinite regions which provide the points that are okay to be used, and we ignored the region in the middle, in this case, which provided the points that cannot be used. Now, is there a way for me to actually shade this in reversed order? The answer is yes. All I need to do is to write 3 minus xy under the root. Then we will shade the middle and not shade the other two. Right? So, this is not something that you can memorize. This is going to be something that you reason with and say, all right, for a square root, I need positive numbers or 0, so greater or equal than 0. For ln, I am only allowed to have positive numbers, so you just put greater than 0. If you have some kind of a fraction, denominator is not allowed to be 0. Now, is it only one variable or both variables or combinations of them, right? So, goes case by case. And then you have the cases that can trick you into calculating, but if you do a little bit of analysis to begin with, you don't have to do calculations and stuff. For instance, the good example over here would be, say, why is this purple now? F of x equals square root of x squared plus y squared. So you can immediately go and say, oh, square root, so x squared plus y squared bigger than 0, and right, keep thinking about those kind of things, but hold on.
It doesn't matter because
It doesn't matter because they're both squared, exactly. So if you plug in a negative number or positive number, the squares will always return positive numbers. And when you add two positive numbers, you always get positive number. So all of the numbers are cool, positive and negative. Now let's test 0. If you have 0 and 0, well, square root of 0 is still 0. So all points of R2 are the domain. You cannot come up with a value. You cannot come up with x comma y that will make this negative under the root. There's no way. Another example similar to this would be, let's say, f of x of some blah over here divided by x squared plus y squared plus 1. That's another all, provided that blah is nice and cooperative, all of r squared. Because you're not allowed to have a 0, but plus 1 takes care of that. And then whatever you have, negative or positive number for x and a y, they will always square into a positive number. So you are guaranteed never to get a value less than 1 in this particular case. So for domain, just employ some common sense, and few of those tricks that you know from pre-calc now, just apply it to the 3D environment. Some of the functions that you will be sick of by the end of the course would be z equals x squared plus y squared. That's your paraboloid. It's not elliptical, it's going to be a circle because the coefficients of x and y are the same. So that's your paraboloid. Looks like that, right? We have seen this last week. We have seen this equation as well last week. And as you remember, I said you remove y squared, you get z equals x squared, which is parabola. You remove x squared, you get z equal y squared, also a parabola. So that one you are going to see a lot. Many examples will have this one. Another one that shows up is half of the sphere. You see, sphere is not a function, right? Because if you do a vertical line test, it's going to have, for every x and a y, it's going to have two values except at the equator. So it fails to be a function. But half of the ball, right? Half of the ball, which is just let's say the northern hemisphere, it is a function. So if you have x squared plus y squared plus z squared equals to, let's say, 16, this is a ball radius 4, and here in blood, not a function. Why is it not a function? If you solve it for z, you will get plus minus square root of 16 minus x squared minus y squared. So not a function because of the plus minus. But then if you just take the upper half as z equals square root of 16 minus x squared minus y squared, then now it is a function. So it's Again, right, what it's called, vertical line test, there we go, can be used to determine what is a function and what is not a function. The next concept that we study is level curves. Level curves. So level curves help us visualize the function when we don't have graphing utility to help us graph the third-dimensional graphing utility. So, and it's something that it's used actually in engineering a lot, but it's also used to show the terrain on a map. So if you ever read a map, and if you ever seen a map in your life, you see all of these lines that go through the map. I'm just going to enhance this image that we have in a textbook. Let's see if resolution is good enough to, well, you can see it. So this is the map. And let's say you are an enthusiast and you want to drive one of those four-wheel motorcycles, whatever they're called. What are they called? Quads, thank you. So you have, you're a quad enthusiast. I mean, you would not have this accent, obviously. It's more southern accent. And you want to drive it. You pick the map. We are going to learn very soon that when these lines are very close together and dense on a map, the incline is very steep. It's also very important for military, because military is always off-road. You don't see military trucks and tanks and stuff driving on the highway, right? Ripping it up. They're always in dirt, in forests, and on fields, right? So when you're going from point A to point B, yes, you are driving a tank, but you still can't drive a tank on the 80% incline. So to drive a quad or a tank or whatever off-road vehicle you have, this is where you are okay. Because these, when the level curves are far apart, that shows that the terrain has very little variation in height over distance. When they're very close together, that means there is a very steep incline and you will not be able to. So if you are a rock climber, you are looking for this, right? If you are driving stuff around, even biking and stuff like that, you are not looking for a terrain that it's 80% incline. So now, how do these level curves help us in terms of figuring these things out? Well, let's take a look at the shape. I told you you'll be sick of this. Z equals 9 minus x squared minus y squared, which is the paraboloid that opens downward. All right, so it's like an umbrella. Would you like mine? So now, what I have here is we first draw like a Taco Bell over here. And then we draw axes. We have our x, our y. The peak over here is at 9. And now, what I'm going to do is I'm going to create level curves and graph them on xy plane. So, level curve for z equals 0. That's a floor, right? Z equals 0 is a floor. In our classroom, z equals 10 is the ceiling. So z equals 0 is the horizontal plane, which is our xy floor, xy plane. Now, when I plug z equals 0 into my equation, 0 equals 9 minus x squared minus y squared, I get a circle x squared plus y squared equals to 9, which is something that I can graph. That's a circle with a radius 3. And then I can say, okay, so what's the level curve for z equals to 1? Well, you plug in 1 equals 9 minus x squared minus y squared, and you get x squared plus y squared equals to 8. You get another circle that goes through square root of 8. Because your radius now is square root of 8. Level curve for z equals to 2. They're evenly spaced. You cut at every unit. You cut at every mile. You cut at every inch. You cut at whatever scale you come up with. So now 2 is equal to 9 minus x squared minus y squared when you plug in. X squared minus y plus y squared is equal to 7. That's another circle. And then negative root 7. So root 7 as a radius. So we have these concentric circles that are climbing up. And we can imagine we are a bird that it's flying above the object. Because if you have umbrella open, right, you as a bird from the top, you only see a circle, right? And then with a better eye, you would see the shade, right? And you can pick up the shape. You still see a circle, but the shade and reflection of the umbrella and all of that stuff would suggest that it is like a dome, which is what we have in this case. Let's go to my favorite example. Now, this is potential function, electrical fields and stuff like that. But you know what? Let's not worry about physics. Let's just call this termite nests. All right? Have you seen termite nests like this on TV ever, or a movie or whatever? Right? So let's put it that way. What are you going to get as you start slicing with z equals a number of parallel planes? You are going to get for the top, right, two little circles, right, that will keep widening and widening and widening until it starts writing eights and then peanuts around eights. Now, I really need you to stare at the two images side by side, the pair of these termite nests and the level curves, and see that whenever level curves are dense, you have a steep, very, very steep climb. And then when they're not so close by, you have this flat. It's still curved, but it's not as steep. You saw the example, right? You know which way to find this. If I give you the equation for this termite nest, you will be cutting this with z's, and whatever equation you get are these functions that you get to draw. But the most important part for us to learn from this example is that anytime these lines are very, very close, the shape has the steep, what we call ascent or descent. And then when they are far away, further away, you have flatter piece. It's still curved, but it's flat. This lecture is a lot of looking at the pretty pictures rather than calculating. You saw the calculation, very simple, right? Plug in and be done. Let's see other level curves. So here is the one that I did already. Now we see a pretty picture of it. This is the this is e to the negative x squared minus y squared, but it almost looks like what I have done. And you can see the circles because this is like a cone or like umbrella. The umbrella is not really like that, but you can make it better if you want through the equation. And you see that these circles here are uniformly, right, getting larger and larger and larger. And then you see that these circles at the end getting more distance, but then you see how it flattens here. These types of models are actually used. I have seen them on seminars at NGIT when people talked about geometry of cancers. And they were talking about geometry and diffusion models and all of these kind of things. So you have something that looks like this, and then there is an extra ring going around that can be also detected through the level curves. So it's easier to look at that image than the 3D generated image there. And then depending on how these circles go, you know whether surgery needs to happen to actually remove the growth. These are the things that are actually studied. It's not just pretty pictures. They actually, a lot of these have purpose. Another one, that's a wave, 3D wave. Talk about the ocean, right? You want to talk about Navy. It's important. Look at the level curves, just parallel lines. It gives you a wave. So it's cool. And here is another example for the probability function, for instance. Again, you get the function, you plug in different values of z, it comes up with different functions, x, y, which you graph. You can fold the paper and put it on an incline and get this shape. See? You fold the paper like that, and you put it on the incline like that. There you go. You can create this shape. And now as you cut this way, you get all of these nesting parabolas. It takes some 3D mental power to render these images in your head. It's not impossible. And the way I like to think about these is, because I like to cut the things with a sword, if you make horizontal cuts on the equal distance, whatever the cut is made, that's the line, and you just compress all of those on a graph, and it gives you XY graph. Oh, there's my surface that I was looking for. Except this one is elliptical. Mine was circle. This one is elliptical. So when coefficients in front of x squared and y squared are not the same, you get the elliptical one. So for level curves, we want to cut with the equally distant planes. So you pick whether it's z equals 1, 2, 3, 4, 5, or z equals 10, 20, 30, 40. They need to be equally distant. And then whatever equation, since you are setting z to be a number, you are eliminating z from the equation. And you will have only x and a y. And you will be able to graph whatever you have. And then you keep graphing for each of the assigned values for z, and then you will have the level curves. Where is the cool one? Ah, there it is. Those are four-dimensional images. Color represents the fourth dimension. What would be the fourth dimension? Well, if you look at this bottle, or any of your bottles, I don't care, if this is really, really, really clean water, is that the only requirement that you need to drink it? What else needs to hold in order for you to drink it? Like, you can model yours. Right? So water, so that's clean water, right? And you are drinking it. Under which condition, keeping the fact that it's clean, you would not drink it?
Steam.
Yes. If that water was at 205 degrees, you would not be drinking it. So there's your fourth dimension, temperature, in this case. We can talk about density, change the state of that water to ice. Can you drink it? No, you can't, right? It's ice. You don't get to drink a block of ice that's bigger than your mouth. You can't. So we can actually have higher dimensions as well.
How can you have a function that's two-dimensional input and a two-dimensional output?
Yes.
That's what it looks like those are graphing.
Yes. Two-dimensional input, two-dimensional output. You can have whatever dimensional input into whatever dimensional output, depending on what you are tracing. Because your application drives what you need. So far, all of the mathematics you have seen so far, all the way through Calc 2 and so far in Calc 3, you had single-dimensional output and single-dimensional input, right? The functions we covered today were two-dimensional input as a location, and then it maps and gives you a z value somewhere, and that was one-dimensional output. But you can have multi-dimensional output. The output of this tablet right now is to the projector, to my screen, and to YouTube at the same time, right? It's three output values from the same input, which is this, right? So you can have a single variable driving two, two variables driving one, multivariables driving multivariables. You can have all of these things. It's fine. You just need to know what you actually want, right? So if we are talking about this four-dimensional case over here, what I'm going to have in this case is 3-dimensional bottle, which is containing the water, and then I can talk about density of the water, which could be water, could be blood, it's different density, right? Or I can say, okay, don't worry about density, let's talk about the temperature of it. That's another, right?
In the case of either of those, though, temperature or density, wouldn't it be a 3-dimensional input, 1-dimensional output still?
Yes, it would.
Okay.
Mm-hmm. So 3-dimensional input in terms to confine the space in which, right?
I'm just having trouble, like, visualizing, like, the mathematical part of, like...
Oh yeah, because you don't deal with 4-dimensional concepts, right? We can put space-time, right? You have 3 dimensions of space, 1 dimension of time, and in order for you to be in class, all of those have to match, right? Your location X, Y, Z in the universe where you sit, and you have to be here at 7:30. Otherwise, it really doesn't work the other way. Right.
It's more the multi-dimensional output that I'm having trouble with, like understanding.
Because of the complex variables. If I have let's say I have a function ix plus 3, that's a function, right? And I give it ix plus, let's say ix plus 3x, whatever, doesn't matter. And I give it the input x equal, no, let's just do ix plus 3. And I give it the input of 2 plus I. This is a 2-dimensional output. It has a real and imaginary component. Complex numbers are 2-dimensional numbers. See, okay, but this is the reason why you didn't, right? So that's why it's difficult, because you haven't had mathematics that dealt with these kind of things. So now if your function over here of x is given this way, then when you plug this number, you have I times 2 plus I plus 3. This is I plus 2 is, I times 2 is 2I, plus I squared plus 3, and this is negative 1. So you get 2I plus 2, so 2 plus 2I. So your input was 2 plus I, which was a 2D, and your output is 2 plus 2I, which is also 2D altogether, 4D.
So the key is having values that don't interact with each other as smoothly as we think of numbers.
And yeah, and so we have to use color to bring in, because we are okay to visualize even the 3D on a 2-dimensional space, right, on a 2-dimensional surface. If I draw this, you can all guess what it is, right? What is this?
Cube.
A cube. It doesn't take you long. If I draw this, you know what it is. What is that? A sphere, a ball, right? Like that. Is that actually a ball? No, it's not, right? It's the representation of it on a 2D surface. It's a drawing, it's a 2-dimensional drawing. But we can perceive it as a 3-dimensional, Now, we can draw a 3-dimensional representation of the 4-dimensional cube on 2D. 4-dimensional cube, the tesseract, hypercube, right? If you can draw that as well. You draw a little cube, and then you draw a larger cube around it, and then you connect the corners, and then there will be one in the back. And that's 3-dimensional representation of the 4-dimensional object on 2D surface. That thing has 8 cubes that are all same size. Because this side here is A, and this side here is also A. But in a 4D space, they're all, because you have an extra dimension. Now, we live in a 3-dimensional space, so 4th-dimensional space really bothers our brain a lot. Because as a three-dimensional creature, if you are locked in a four-dimensional cube and you put your arm through that wall, it comes out from that wall. Yeah. So you have to.
And this is proven how?
It's not proven. You just.
It's all theory.
You're just no, not even theory. You trace the coordinates. You can put the coordinates. You have 4 of them, right? You pick a 0, 0, 0, 0 location, and then you go 1, 0, 0, 0, or this way 0, 1, 0, 0, the other way, right? So you can go in 4 directions, and I did that for my undergrad. One of my undergrad talks. It was a lot of fun, and you can warp. See, the trick is, for instance, I posted on my Instagram some time ago, when we have, I don't know, whoever is coming to campus, right? Our security guards put these cones for the parking lots, like this, right? And they think you can't park. But what they don't account for is that the line on the ground is a 2-dimensional line painted on the ground. My car is three-dimensional, so it fits right here. Problem solved, right? When you think about dimensions, 3D always wins. You can't have, it's like, okay, let's make a prison, and you just draw a square on the floor, and you just put the prisoner right there in the middle. Like, really? Just walk out. That's the equivalent of this. Put a little cone in the middle. Like that's, They upgraded since, and then they stretched the do not cross to the yellow. It's not heavy or anything. Drive under that thing. It's easy. So, talking about the dimensions, you can have any input, any output. Depends on application. Depends on what you need to get. Now, for most of the complex variables, we use it theoretically because the world is real. But the complex variables have this great feature where you multiply 2 complex values to get a real value. Now, a lot of people are bothered by that, but then complex is just an unfortunate word for a 2-dimensional number. It was complex in a time when they thought of it. Today we have hyperdimensional numbers used for computer science, but your complex number 2 plus 2i is nothing more complex or imaginary than number 7, because you don't see number 7 walking down the street, right? It's a mathematical construct, just like 7i is a mathematical construct. And then we put 7 plus 7i, and now we want that to be something special. It's not. So you can come up with whatever dimension numbers you want, and that determines the space you will be working in, and then you can build up mathematics. So 2D input, 2D output would be a 4D space, and we need color, so we can keep our 3D, and then plus the color. Usually red, right, signifies very hot, and blue signifies very cold. So you can encode temperature as the 4th dimension in that way. And then you have a whole bunch of these examples to find the domain, to calculate your level curves by setting z's equal to whatever value. Anytime you see f of xy, p of xy, g of xy, you replace them all with z, because it is z equals the formula. And as you assign values for z, you can get your level curves. That's it. Bye.